All right, guys, so rather than move on to our next thing, I figured that we might as well do like a little practice day of the 2 formulas, or really 3 formulas that we did this first week of the distance learning stuff. So what we did earlier in the week, we started off by doing exponential growth and decay on the same day, and then you did some practice questions, and then we did half-life, and then you did some practice questions. So now I'm going to give you some practice questions that include both of them. So you have to know when to use what. Okay, so on the top of this worksheet, I wrote down the exponential growth formula, the exponential decay formula. Again, those are pretty much the same formulas, except when it's a growth, you have plus R, and when it's a decay, you have minus R. And then we have the half-life formula as well. Okay, so you have in your notes what all of those variables mean. So if we start with number 1, it says the population of garden snakes in Center Reach, New York is decreasing at a constant rate of 4.3% every year. So it's decreasing at a constant rate of 4.3%. This is an example of exponential decay. Okay, so you're going to write the exponential decay formula down. That way you're not even worrying about what formula to use. A equals P, 1 minus R raised to the power of T. Okay. If there are currently 345,200 garden snakes in Center Reach, algebraically determine how many garden snakes there will be in 15 years rounded to the nearest whole snake. So if we just go over this quickly, A is a future amount, P is the current amount or initial amount, R is the rate, and T is the time. So the question is how many garden snakes there will be in 15 years. So how many garden snakes there will be. So we're looking for the future amount of garden snakes. The future amount is your A variable. So we are solving for A. Solve for A. So if we're solving for A, we have to plug something in for P, something in for R, and something in for T. P is how many garden snakes there currently are, or your initial amount. So that's going to be the 345,000 number. So 345,200. R is the rate. It's decreasing at a constant rate of 4.3%. Remember, whenever you're plugging in for the rate, you move that decimal over 2 times to the left if it gives it to you as a percentage. So 4.3% is really 0.043. And the time, we want to know how many snakes there will be in 15 years. So T is 15. Okay, so if I plug all of this in, this is going to look like this. A equals 345,200, 1 minus 0.043 raised to the T power is 15. So now with these equations, you either have a very easy time solving for them, or you're going to have to use logarithms. You use logarithms when the variable is up in the exponent. Okay, in this case, the variable is by itself on one side of the equal sign. So in order for us to solve for A, all we have to do is plug that into the calculator, exactly how you see it. Make sure 15 is an exponent. We are rounding to the nearest whole snake. So when I plug that into the calculator, I get 178,546 if you round to the nearest whole snakes. Now that also, keep in mind, this is exponential decay. So that makes sense because the 178,000 is less than the 345,000. Right? If you got something that was more, that would be a problem because the amount of snakes is supposed to be going down. Okay? And that's it. That's it for number 1. For number 2, it says element X is a radioactive isotope such that every 13 years its mass decreases by half. That is the definition of half-life, how long to decrease by half. So because this is your half-life, I want you just to write down the half-life formula. before you even keep going. Okay, that way we're trying to get rid of all the wordiness, so that's why I do this stuff on the left side where I write what variable you're solving for and then what everything else is. That way it gets rid of all the wordiness because no one likes word problems, right? So this says, given that the initial mass of a sample of it is 8,800 grams, algebraically determine how much of the element would remain after 25 years. So we are looking for a future amount. How much of the element would remain, right? A future amount. The future amount is your A value. So again, we are solving for A. So we have to plug something in for P, which is the starting amount, something for T, which is how long it's been, right, the time, and something for H. Now, H is also a form of time, but it is specifically the half-life. So as we start rereading this, it says that every 13 years, its mass decreases by half-life. That means that the half-life is 13 years. Given that the initial mass of a sample is 8,800 grams, so your p-value, you're starting off the initial amount, 8,800 grams. Algebraically determine how much would remain after 25 years. So it's going to be 25 years. And then you plug all that into your formula. So we have A, stays A, because that's the one that we're solving for, equals 8,800 times 1/2 raised to the time divided by the half-life. Now again, I have to see, do I need to use logarithms? Your variable is not up in the exponent, which means you do not use logs. And again, your variable is on one side of an equal sign, so you're just going to plug 8,800 times 1/2 raised to whatever into the calculator. That gives you, and we're rounding to the nearest hundredth of a gram. A equals, we get 2,320.49 grams. 49 grams. And that's your answer. That's a G, not a Y. We're not talking about years, we're talking about grams. And that's it, okay? Number 3, carbon-14 has a half-life of 5,730 years. Carbon-14 has a half-life, so this is a half-life question. A equals P times 1/2 raised to the T divided by H. I suggest you try to commit these to memory, even though I know everything's at home right now, so you can always look through your notes. Just know that in Algebra 2 next year, you're not given these formulas on a test or on a reference sheet for a test or anything like that, so you need to know the formulas. All right, so if the initial mass is 240 grams, algebraically determine how long it would take. So we're looking for a form of time. So our form of time is between time or half-life. We know what the half-life is. The half-life is 5,730 years. So that means that we are solving for T. We need an A, we need a P, and we need an H in order to do that. So if we reread the question, carbon-14 has a half-life of 5,730 years. So H is 5,730. The initial mass is 240. So the p-value is 240. And we want to know how long it would take for the mass to go from 240 up until 180. So we want A to be 180 grams. So when we go to plug all this in, we have 180 is our A value equals 240 times 1/2 raised to the time. We didn't plug anything in for T because that's what we're solving for, divided by H, 5,730. Okay, so this is our new equation. So if we look at this, our variable is up in the exponent, so we're going to have to do logs. So the first step in using logs is to get the base and the exponent by itself. So I divide both sides by 240. 180 divided by 240 gives me 0.75 equals 1/2 raised to the t divided by 5730. Now we're going to take the log of both sides. So the log of 0.75 equals t divided by 5730, log of 1/2. To get the variable closer to being by itself, we divide both sides by the log of 1/2. I know this looks kind of messy. Divide by the log of 1/2. So I'm going to bring this up here just because it looks ugly. So I'm going to bring this up here to get us a little bit more space. So when I do in the calculator log 0.75, close the parenthesis, divided by the log of 1/2, that gives me, you're writing 5 decimals, 0.415, 41503 equals, and then on this side the logs canceled, so it's just t divided by 5730. Okay. Once you get to this step, you are always going to cross multiply. So I put this under 1 and I cross multiply. 1 times t is t equals, and then you do that 0.41503 blah 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 times 5730. And then what you get in the calculator is going to be your final answer. So then you can round that. Nearest tenth of a year is 2,378.2, and that's years that we're talking. Okay? And that's it. Next, let me erase some of this that ate into this last question. All right, next. An isotope of fluorine is one of the radioactive isotopes that are used in nuclear medicine to diagnose and treat disease. A patient is injected with 250. After 2 hours, there's 118. Algebraically determine the half-life. So again, we're talking about half-life, so I write down the half-life formula. That way it's one less thing to have to worry about. Raised to the t divided by h. The question very specifically says that you're finding the half-life. So you're solving for h, which means you have to plug something in for a, for p, and for t. So again, P is how much you're starting with, A is how much you're ending with, and T is how much time has passed since you've gone from P to A. So a patient is injected with 250 milligrams, and after 2 hours, which means that T is 2, there are 118. So that's it. 118 is A, 250 is P, and T is 2. Solve for H. So again, by doing this, you're getting rid of all of the wordiness. So you have 118 equals 250 times 1/2 raised to the t divided by, raised to the 2 divided by h. Because we know that t is 2. 2 divided by h. Okay, so again, your variable. Again, I'm zooming in because I really don't even need the word problem anymore, other than to know that I'm rounding to the nearest hundredth. Your variable is part of the exponent, which means you're going to need to use logs eventually. So first, you divide both sides by 250. 118 divided by 250 gives me 0.472. Equals 1/2 raised to the 2 divided by h. I take the log of both sides. Log of 0.472 equals 2 divided by h, log of 1/2. Divide by the log of 1/2. On the left side, when you actually do that division, you get 1.08. 1.08314, again 5 decimals, but you keep the whole number in your calculator, equals 2 divided by h. Again, once you get to this step, you're going to cross multiply. 1 times 2 is just 2, equals 1.08314. 0.8314H, and then you divide by that whole decimal to get H by itself. Make sure that you're doing this in the right order. You're not doing the 1.0314 number divided by 2. It's the other way. 2 divided by 1.08314. So this will cancel over here, which gives me H equals, now you can round to the nearest hundredth because this is going to be your final answer. You get 1.85, and that is talking about hours. That's your answer. And last one. So this one's a little different. I can already see why, because this gives you an equation that's already, everything's already plugged in. So the growth of a particular bacteria can be modeled by that function. T is the time in years, A is in grams. So it's the same setup, it's just that things are already plugged in for you. Rather than saying it started off with 3,000 and it's a growth by 5.8%, it gave everything to you. So the question, so again, you don't even have to write the formula, you just can rewrite this. This is what you're going to use. Algebraically determine how many years it will take for the bacteria to reach 4,500 grams. So between A and T, how many years you're solving for T? So you're solving for T. If you look in this equation, that means that you would just have to plug something in for A, which is the 4,500 grams. It's the future amount. So we have 4,500 equals 3 grand times 1.058 raised to the T. Your variable is in the exponent, so you need logs. So you divide both sides by 3,000 to start. You get 1.5 equals 1.058 raised to the T power. Take the log of both sides. Log of 1.5 equals T log of 1.058. Divide by the log of 1.058. This will cancel over here, so I get T by itself equals, we are rounding to the nearest hundredth, so final answer is 7.19 years. Okay? So that's it. So next week we're going to pick up with the other two equations, but on Monday you're going to do some practice of these. It'll look exactly like this. Do not wait until 11 o'clock at night to do it if you're struggling. That way I can help you and answer any questions that you have. Okay? Let me know if you have any questions. Have a great weekend.